disruption, Farmer John has n pastures with n-1 bidirectional pathways. He's going to go through each one of these pathways and remove them. He also has m additional bidirectional pathways. These are only going to be used if one of the original pathways are blocked. So for each one of the original pathways on the farm, we need to find the shortest replacement pathway of the m additional bidirectional pathways that will basically allow the farm to be fully connected again. Let's go look at the algorithm for this question. We know that this graph is going to be able to be formed as a tree. So in order to basically solve this question, we can make a couple observations. First, let's say we have an edge between node A and node B. So for this edge, if we look at this graph, when we split off an edge here, then only the edges in that subtree are able to be used in order to connect the subtree back to the main tree. For example, if we cut off this here, then only the edges in this subtree are able to be used. And using that logic, if we have A and B with an edge in between them, then if and only if A and B are part of two different subtrees, will this edge be useful? So if an edge here is cut, then this and everything else will be a different tree, so it'll be useful. And then if, say, this is cut, then this and everything else will be a different subtree, so it'll be useful. But in the case where this is cut, where they're in the same subtree, then this edge is not useful. And the specific place where edges start basically being not useful is when these two are in the same subtree. And if we denote every edge as the node underneath it, so this edge belongs to this node, this edge belongs to this node, then we can assume that at the point of the least common ancestor between A and B, and in this case A and B, it's here, any edges underneath that, this edge here is going to be useful. And then any edge that is above or not part of that, then this edge is not going to be useful. And what that does is this edge is going to be useful only for the edges from A to the LCA to the B. And so if we were to kind of brute force is, for every edge we just find its A and B, and then we find its LCA, and then for every edge from A to the LCA, and then from B to the LCA, all of these different edges can use this edge here as a potential replacement in order to fully connect the graph. So if we just directly use this algorithm, basically LCA, find, and then use every edge, and for each one of these edges, its answer value is the minimum of its original answer value, and then this new edge here, then what we can do to speed it up is we can actually use DSU, or disjoint set union, or union find. And the way that works is we're going to sort our edges from smallest to greatest. And once we've sorted them, we're basically going to realize that once an edge is assigned a value, or since we're looking from edge to edge, if we find the edge with the smallest value, and then we assign the different values, then whatever values get assigned, they're not going to be able to have a better answer, since this is the shortest possible edge. So what we can do instead is we can basically look at our path, and then instead of going from A, up one edge, until we reach the LCA between A and B, we can look at this as which edges have not yet been assigned. For example, from our path from A to the LCA, this way up, we can check to see if this edge has already been assigned, then we no longer need to make it the minimum value of itself and this edge, since we're going from smaller edges to larger edges, meaning that whatever value this is, if it's already been assigned, it's going to be greater than our current edge. So what we can do is we can actually use DSU to combine the edges together. So these, let's say we assign this the value 3, 4, and then we're at this current node A. So what we can do is, if an edge has already been assigned a value, we're just going to merge it with its parent. And so once these are merged, then what we can actually do is we can use a sort of leaping up method, kind of like binary jumping, but not really, where we go from A and then to A's root, and then from A's root to A's root's root. And that way, we basically clump any node that isn't the root together. So like, if we have a node here that's already been assigned, we're just going to merge it with its parent node. And that way, in any future scenario, this node here is never going to be the root. And since it's never going to be the root, we're never going to assign its edge. And then so we're just going to jump directly from node to its root, and then to its root. And that way any edge that's already been assigned is never going to be the root, and is therefore never going to be assigned a new value. So that's the basic idea for the algorithm. Let's go look at the code for a more in-depth explanation. We're going to start off with values and then a couple data structures. I'm going to create a struct called edge, which is going to store 3 values. It's going to have the 2 nodes and then the weight of the edge, and we're going to use that to store our replacement m edges. After that, we're going to store a couple different vectors for our DSU and for our LCA. So for our DSU, we have the root, which is going to basically store the root of every node. And then for our LCA, we have our up vector. So that's going to store the parent and then the binary jumping for every node. We're going to read in our edges, and then we're going to do an initial DFS. So this DFS is going to give us the up vector and then also our depth. So this is going to be a very typical DFS. And then we're going to first find the depth of every node. And then we're going to initialize our jump table, or the up vector. And this is just binary jumping. And then we're going to loop through our children like in a normal DFS. Once we've done that, we have the values we need, and we can start reading in our m replacement edges. So we're going to read them in, and then to optimize, we're going to sort them by their weight. So we're going to use this to sort, and then we're going to loop through them. So for our DSU part, we're going to resize our answer vector and then basically fill in all of the values that we need. And then we're going to start looping through. So the brute force version of this question is we're going to find for every 2 nodes the LCA, and then we're just going to literally loop from node A up to its parent, and then up to its parent, and then to its parent, and up until we reach the LCA. And then for each one of the nodes, we're going to assign the answer of that node as the minimum of itself and the edge weight. Since this current edge can be used for anything from the node to its LCA, then we're just going to literally loop up every single edge and then assign its own value as the minimum of its current value and then this current edge. And then we would do the exact same loop, but for B. So that's the brute force. It passes around 9 test cases. But if we don't want to brute force, then we use jumping. So this jump function here is basically going to go through, and it's going to use our DSU. So over here, we're going to have 3 different parameters. We have our node, the LCA, and then the weight. So for DSU, we're going to have 2, or actually 1 main function since we're going to optimize it, which is just going to be find root. So find root is going to just do what a normal DSU does, and then it's going to also assign at the same time. So this is like a both update and query function. We're going to assign R as the root of itself, and then we're going to keep looping up. So this is effectively going to skip all of the nodes that aren't the root. So it's going to jump from the node to the node's root, and then from that root to its root. And the reason we do that is because when we want to optimize this, since we already sorted the added edges from the least to the greatest, then if something has already been assigned or already been visited, we don't need it anymore. So we're just going to, basically as I described earlier, we're just going to merge it together, and then it's not going to be something that we need to assign. So we're only going to be jumping from node to root to root to root. And then once a node has been assigned, it's just going to be merged so that we never touch it again. So with the jump function, we use find root, and that's the majority of the DSU part. And then for the LCA over here, which is also needed in the brute force version, it's going to be a very standard LCA. So in this case, I used my up table, so we have our binary jumping here, and then this is very stereotypical code. Once we've done that, we basically have our two versions here. Again, the brute force 9 test cases, and then if we use the DSU, it fully passes. We're just going to print out our output. I'll just loop through, use our edges list, and then a thing here is, since we have two nodes, our depth is basically going to allow us to see whether or not something is the parent or the child. And since we want to output the node or the edge corresponding to the node that is the child, we'll just check to see whichever edge is greater. And then whichever edge is greater is the child node, so we'll just print out the answer there. And then another actually small important thing is in our brute force, over here we're going to keep jumping up, and then our parameter is going to be based off of the depth, just in case, because I used a for loop, just in case the node is equivalent to the LCA, this is just going to allow us to make sure that we end up getting it in. So with our brute force and our DSU version, both of them work with LCA. The code is a bit long, but it basically follows the normal algorithmic structures. And that's the end of our program.